now what is left is just algebra. Algebraic manipulations in order to get the result. Okay, so here we have to make a trick and multiply by lambda. The lambda to the power x is what is going to work in here, and you will see why. So if we multiply and divide by lambda to the power x, which is multiplied by 1 to the power x, we can simplify this expression as follows. Now, p and lambda are raised to the power x. So we take advantage of that and write this as follows. So this is going to be lambda p to the power x, and then e to the minus lambda. That doesn't depend on the y, so we can take it out, e to the minus lambda. And then, this is a second trick. We take the first one out, x factorial. Remember that we start in here, and then we have a sum here of 1 minus p times lambda to the power y minus x, and here y minus x factorial. Okay? From y equal to x to infinity. Okay, let's see where we get this from. So, e to the minus lambda is here. Lambda p to the power x is here. So, e to the minus lambda is okay, here we have y minus p, y minus x. Now, in here we have lambda to the power y minus x. Okay, so here is lambda to the power y minus x. Are you with me? Fine. Okay, so now we have here y factorial, can give out. This is also here, These have been taken into account. This is y factorial. Now we have y minus x factorial, that's the other term, and finally we have an x factorial, which is the one that we take this here. Okay, so this expression can be simplified into this expression. Are you with me? Any term left out? Doesn't seem like it. Okay, so we can continue. Now, this is, we can be written as lambda p to the power x, e minus lambda, and then x factorial in here, and here we have the sum of t equals 0 to infinity of 1 minus p multiplied by lambda to the power t divided by t factorial. Why is that? Well, you see, in here we are working with y minus x, and here y minus x. So, and this is starting y equal x to infinity. So this is starting 0 factorial, and this is 0. So if we make the substitution y minus x equal to t, this t will go from 0, which is in y equal to x, to infinity. So we put t factorial here, and here the power t. Okay? To the power t. Now, and this is a series that we have found already in this course. So this is going to be equal to e exponential 1 minus p times lambda. So e to the lambda 1 minus p. Okay? One way to see that is that if we make a Taylor expansion of this function, this is the expression that we want to have. In fact, this is the expression that makes e to the minus lambda also the proportionality constant of the Poisson distribution. Okay? So this is going to be e to the lambda 1 minus p. So, all in all, we're going to have lambda p to the power x divided by x factorial, and here we're going to have e to the minus lambda, and here e to the lambda 1 minus p. Okay? And so this we have here, so we're going to have in the exponent minus lambda, and then minus lambda p. So this is going to be lambda p power x e to the power lambda p, and this divided by x factorial. This is the final expression. I repeat, it will be lambda p to the power x e to the power minus lambda p x factorial. This should be familiar. Okay? This x is from 0 to infinity. So, what do you think this is the distribution of? It's not Poisson, thank you. Poisson, with which it's not Poisson. What is the parameter? The parameter is lambda times p. So, the result is that if we have, say, a model that lays yx, and from those x survive according to a binomial distribution, the resulting random variable, which is the number of survivors, is going to be another Poisson, but now instead of having parameter lambda, we're going to have parameter lambda times p. Okay? And that's very natural. Listen, very simple, very natural. If p is equal to 1, so all are survivors, when the number of survivors is going to have a Poisson lambda distribution. But if p is equal to half, for example, just half of them survive, we're going to have a Poisson with half the rate, lambda of Poisson, with half the mean of Poisson. Exactly, that is the result that motivates this huge area of mixture models and hierarchical structure of random variables. So this is the best motivation we can give, and we will continue this in the following class.